Good morning, everybody. Before we start, we must convey our deep respect towards the health workers of India, the doctors, nurses, the sanitized workers, also the policemen, towards their contribution of the health and wealth of the country. Okay, today we will discuss the conformation and stability of cyclohexane. Okay, see, this is the model of cyclohexane. Each of the guava represents the carbon atom. But since all carbon atoms are single bonded and sp3 hybridized, the bond angle should be 109.5 degree, which cannot be maintained by this flat or planar hexagonal model which shows 120 degree bond angle. For this reason, it assumes certain non-planar structures where it maintains bond angle around 109.5 degree, which is known as the chair conformation. Okay, in the hexagonal structure, take this carbon down, okay, and this carbon up, okay. Thus, you get the cyclohexane structure in the chair form. Okay, you see, this is the structure of chair form. Now, this is the head, okay, and this is called the footrest of the cyclohexane structure in chair form. Okay. This chair conformation rapidly interconvert to a similar other chair conformation in which the footrest and head are interconverted. This interconversion from one chair form to another called the chair flip. This chair flip passes through three other conformations. The full transition from one chair form to another occurs like this. Let us now see how the cyclohexane in its chair form passes on to different other forms, other conformations. Okay, lift this carbon up and then see how you are getting the half chair conformation. Okay, now in this half chair form, take this carbon up. Okay, this carbon up so that you get the boat form. Okay, let us see. This is the boat conformation. The carbon atoms are numbered in this way: 1, 2, 3, 4, 5, 6. Hold the bond joining carbon number 2 and 3 in one hand and hold the bond joining carbon number 5 and 6 in the other hand, and then twist this bond the way I am showing. That will result the twist conformation of the cyclohexane. Okay, one most important thing to be realized is that during the chair flip, the axial hydrogen atoms becomes the equatorial
and vice versa. Look at the top left chair form of cyclohexane. The hydrogen indicated in red is the equatorial hydrogen, which is perpendicular to the axis of symmetry or horizontally placed to the ground. And the one indicated in blue is the axial hydrogen. You see, in the first operation, from chair to half chair, the equatorial hydrogen remains the same equatorial in the next half chair form. In the next operation, when the half chair is converted into twist boat conformation, the hydrogen which was in equatorial position in the half chair form has been converted into axial position, and this trend continues in the series of next operations, and when we reach at the inverted chair, which is at the bottom left, the hydrogen indicated in red is the axial position. Now this is clear that the equatorial and axial hydrogen atoms are interconverted in the chair flip. Okay? Now let us discuss the stability and energy content of different conformers of cyclohexane. Okay? Chair conformation is the most stable form because all the carbon atoms are staggered to each other. This can be shown from the model. See, this is the carbon atom number 1, then 2, 3, 4, 5 and 6. Taking C2 and C3, you see how this and this are opposite. Similarly, this and this are opposite, and also this and this are opposite. Hence, by Newman projection formula, we can show that carbon C2 and C3 are staggered, and so as the other carbon atoms. The cyclohexane molecule can be represented in Newman projection formula. In this projection, we look from the C1 side, that means from the carbon number 1. Thus, the C2, carbon number 2, becomes the top carbon represented as a dot, and the C3 becomes the bottom, which is represented as a circle. Okay. Similarly, the carbon number 6 becomes the top carbon and represented as a dot, and the carbon number 5 becomes the bottom and represented as a circle. Okay. Thus, you see how cyclohexane in its chair form is completely staggered. Also, the angle strain is 0 in cyclohexane, as all the bond angles are 109.5 degree, and hence most stable, least energetic. Okay. In the boat conformation, though there is no angle strain, the C2 and C3 and the C5 and C6 are eclipsed, for which there is considerable strain. Since the two hydrogens at C1 and C4, which are called the flagpole hydrogens, are close to each other, the van der Waals repulsion comes into play. These strain raise the energy of the boat conformation by about 30 kilojoule per mole compared to chair conformation. Hence, boat conformation is less stable than chair conformation. Okay? See again that the boat form, being less stable, relieves its strain by converting itself to a comparatively more stable and less energetic conformation called the twist boat conformation. In this conformation, the plug pole hydrogens move apart, reducing the van der Waals strain. Thus, the energy is reduced. Twist conformation is less stable than the chair form but more stable than the boat conformation. Okay? In the half chair conformation, the strain is so high that its energy is raised to the highest and becomes least stable. Thus, we can say the half chair and the boat conformations are the transition states. The energy relationship of various conformation is like this. If this video helped in understanding the cyclohexane, its conformation and stability, then kindly subscribe to our channel and share the video. Thank you.